Hey there, it's Shannon Mavchick-Myers. Today we're covering section 4.5, Undetermined Coefficients, the Annihilator approach, from the ZIL Intro to Differential Equations text. So recall from section 4.1 that an nth order differential equation can be written as a sub n times that nth derivative of y plus a sub n minus 1, so this is just the different notation, times the nth derivative, n minus first derivative of y, and then we keep it going until we get down to a1 dy plus a0 y equal to g at x, where d to the k is equal to the kth derivative of y with respect to x, where k equals 0, 1, all the way down to n. We can also write the above equation as L at y equal to some g at x, where L denotes the linear, nth order, differential, or polynomial operator, a sub n d to the nth derivative plus a sub n minus 1, the n minus first derivative, plus dot dot dot, plus a1d, plus a0. So factoring operators is where we'll start. When the coefficients ai, where I is equal to 0, 1, all the way down to n, are real constants, a linear differential operator can be factored whenever the characteristic polynomial a sub n times m to the n plus a sub n minus 1 times m to the n minus 1 plus dot 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 plus a sub 1m plus a0. So if R1 is a root of the auxiliary equation, which is what we just wrote here, but it's equal to 0 now, then L equal to d minus R1 times some polynomial in d, where the polynomial expression p at d is a linear differential operator of order n minus 1. It also turns out that factors of a linear differential operator with constant coefficients commute, which is very cool. So let's take a look at our first example. Write the given differential equation in the form L at y equals g at x, where L is a linear differential operator with constant coefficients. If possible, factor L. The quantity 2, and then that's that second derivative. We're going to factor out a y to the right, so we'll hold off on that. Minus 3 times the first derivative minus 2 all times y equals 1. Good so far? And then looking to see if this guy factors, let's see what we would have. We have to have minus a 3D and then different signs. So if we have a minus 2 and a plus 1, I think that gives us what we need. Beautiful. And that's all equal to 1. And that's all we needed to do. Groovy? All right. Now, let's take a look at this one. So, this one would be, we have that fourth derivative minus 8 times the second derivative plus 16. All that is times y, and that is equal to quantity x cubed minus 2x times e to the 4x. All right, so this is actually quantity, that second derivative minus 4 squared times y, and that would equal to x cubed minus 2x, all of that times e to the 4x. Cool, cool? All right, perfect. So, continuing, we have our next bit, the annihilator operator. If L is a linear differential operator with constant coefficients and F is a sufficiently differentiable function such that L at F at X is equal to 0, then L is said to be an annihilator of the function. So a constant function y equals k is annihilated by the first derivative, since the first derivative of a constant is 0. The function y equals x is annihilated by the differential operator second derivative, since you'd have this case. So the second derivative is the derivative of the first derivative of x, which would be the derivative of 1, which would be 0. Groovy? Okay, so the differential operator d to the n power annihilates each of the functions 1, x squared, all the way down to x to the n minus 1, which means that a polynomial c0 plus c1 times x plus c2 times x squared plus plus c sub n minus 1 times x to the n minus 1 can be annihilated by finding an operator that annihilates the highest power of x. The functions that are annihilated by a linear nth order differential operator L are those functions that can be obtained from the general solution of the homogeneous differential equation L at y is 0. The differential operator quantity d minus alpha raised to the n annihilates each of the functions e to the alpha x, xe to the alpha x, x squared e to the alpha x, and on until you get to x to the n minus 1, e to the alpha x. Cool, cool? Now, keep in mind the auxiliary, equation of the homogeneous equation, d minus alpha to the n times y equal to 0, is m minus alpha to the n equal to 0. Since alpha is a root of multiplicity, n, the general solution would be y equals c1 e to the alpha x plus c2x e to the alpha x, and then plus dot 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 plus c sub n times x to the n minus 1 times e to the alpha x. Cool, cool? Okay, when alpha and beta, where beta is greater than 0, are real numbers, the quadratic formula shows that m squared minus 2 alpha m plus alpha squared plus beta squared, all of that raised to the n, has complex roots alpha plus I beta and alpha minus I beta, both of multiplicity n. The differential operator, second derivative minus 2 alpha times that first derivative plus alpha squared plus beta squared, all raised to the n, annihilates each of the functions e to the alpha x cosine beta x, x e to the alpha x cosine beta x, x squared e to the alpha x cosine beta x, and on and on and on until we get to x to the n minus 1 e to the alpha x beta or cosine beta x. And similarly, e to the alpha x sine beta x is annihilated by this guy. X e to the alpha x sine beta x, x squared e to the alpha x sine beta x, and on until we get to x to the n minus 1 e to the alpha x times sine at beta x. Now, note that the differential operator that annihilates a function is not unique. Ideally, we want the operator of lowest possible order that does the job. Cool, cool? All right, so this next example wants us to verify that the given differential operator annihilates the indicated functions. You don't have to verify it all the time, but it's saying show that 2d minus 1 annihilates y equals 4e to the x over 2. All right, so we want to show that 2 times that first derivative d minus 1 annihilates 4e to the x over 2. So if the product 2d minus 1 times the function, which is 4e to the x over 2, if that's equal to 0, then that 2d minus 1 annihilates it. So what is it equal to? Well, we'll get 8 times that first derivative of e to the x over 2 minus 4e to the x over 2, which is 8 times, when I differentiate e to the x over 2, I get 1/2 e to the x over 2, and then minus 4e to the x over 2. And isn't that cool? This simplifies to be 4, so they zero each other out. So check, it works. All right, so now let's check out the next one. We've got 2 times cosine 8x minus 5 times sine 8x. And we want to show that this differential operator, d squared plus 64, zeroes it out. So let's see what happens. So we'll get 2 d squared cosine 8x plus 128 cosine 8x. I'm going to move this over here. And then minus 5d squared sine at 8x. And then 64 times negative 5 is going to be minus 320 sine at 8x. 2 times the first derivative of cosine at 8x, which is going to be negative 8 sine at 8x plus 128 times cosine at 8x, and then minus 5 times the first derivative of sine at 8x, which will just be 8 times cosine at 8x, minus 320 sine at 8x. Now, differentiating again, we will have, I'm going to bring this negative 8 to the 2, we'll get negative 16 times, that second derivative will be 8 cosine 8x plus 128 cosine at 8x minus 40 times the first derivative of cosine at 8x, which will be negative 8 sine at 8x, minus 320 sine at 8x. Cool so far? Okay, so now this will be negative 128 cosine at 8x plus 128 cosine at 8x. Those will zero out. Plus 320 sine at 8x minus 320 sine at 8x, which will zero out. So this is equal to 0, and it checks out. Isn't that amazing? I think it's pretty cool. All right, so example 3. Find linearly independent functions that are annihilated by the given differential operator. Okay, so when you have d to a power, it's going to annihilate anything, any x. So the d squared will annihilate 1 and x to the 1, right? That's the d squared part. Now the d minus 5 part annihilates e to the alpha x. So that would be e to the 5x. And the d minus 7 annihilates e to the 7x. Cool, cool? And that's all coming from these lightning bolts. So see this d minus alpha to the n? That's where I'm getting that e to the 5x, e to the 7x. The d to the n, that's where I got the 1 and the x. All right, so know your lightning bolts. So I'll just show you which one annihilated what. Cool? Okay. So, undetermined coefficients. This was all kind of a preparation for this. Suppose that L at y equal to g at x is a linear differential equation with constant coefficients, and that the input g at x consists of finite sums and products of the functions listed with the lightning bolts. That is, g at x is a linear combination of functions of the form k, meaning a constant, x raised to some m, x to the m times e to the alpha x, x to the m times e to the alpha x times cosine beta x, and x to the m e to the alpha x times sine at beta x. Those are all the ones we went over. Where m is a non-negative integer and alpha and beta are real numbers. Following these assumptions, the annihilator approach is 1. You find the complementary solution yc for the homogeneous equation L at y is 0. Operate on both sides of the non-homogeneous equation L at y equals g at x with a differential operator L1 that annihilates the function g at x. Find the general solution of the higher order homogeneous differential equation L1 times L at y equals 0. And then delete from the solution in this last step 3 all those terms that are duplicated in the complementary solution yc. Found in step 1. Form a linear combination yp of the terms that remain. This is the form of a particular solution of L at y equal to g at x. Substitute y sub p found in this step 4 into L at y equals g at x. Match coefficients of the various functions on each side of the equality and solve the resulting system of equations for the unknown coefficients in y sub p. With the particular solution found in step 5, form the general solution y equals yc plus yp of the given differential equation. So these are the steps. Note, the method of undetermined coefficients is not applicable to linear differential equations with variable coefficients, nor is it applicable to linear equations with constant coefficients when g at x is a function such as g at x is natural log at x, g at x is 1 over x, g at x is tangent at x, And g at x is arcsine at x, or inverse sine at x, etc. We will learn those soon. All right, so here's our next example. Solve the given differential equation by undetermined coefficients. So going step by step, all right, step 1. We want to solve 2y double prime minus 7y prime plus 5y equals 0. The homogeneous equation. This will give us our complementary solution, our YC. So what do? Well, remember from section 4.3, we can write this as 2m squared minus 7m plus 5 equals 0. Well, will that factor? Let's check it out. I bet it will. So you got to have a 2m and an m. We're going to have a 5 and a 1, and we need to have it's the same sign. It'll be two negatives, so they're going to add up to be -7, right? So I believe we're going to have minus 5 minus 1. That would give me my positive 5, and that would give me my negative 7m. And that's all equal to 0. So 2m minus, so that is our step 1. We're good. 2m minus 5 is 0, or m minus 1 is 0. So we get m1 is 5 halves, m2 is 1. So y sub c is equal to c1e to the 5x over 2 from our 5 halves plus c2e to the x. Groovy? All right, step 2, annihilate. L at y equal to g at x. So, what was our g at x? Beautiful. Our g at x is negative 29, which is a constant, right? So, d at negative 29 is 0. So, d annihilates negative 29. So if you apply to both sides of the equation, so we've got our 2y double prime, and we're writing it, as d. So we have 2 times the second derivative, written with d, minus 7d plus 5, okay, equals negative 29, and then we apply that annihilator to both sides. Then we'll get d, 2d squared minus 7d plus 5 is 0. Cool so far? All right. Now, step 3. We want to find the general solution of this homogeneous equation. So, but remember, we can write this in terms of m. And we already factored that one, oops, sorry, got it backwards here. We already factored, remember, from step 1. And so we get M1 is 0, and we'll get M2 is our 5 halves, M3 is 1, and so y is equal to, for the M1 equal to 0, we're just going to get our constant 1 plus C2 times e to the 5 halves times x plus C3 times e to the x. Now this one here was from our complementary equation, and then this here is going to be our particular solution. So next step is we need to form a linear combo of our particular solution terms. And it turns out in this case we only have one term for our particular, so we would let yp be equal to sum a. Now, putting together that original equation, which was 2y double prime minus 7y prime plus 5y equal to negative 29, we would have, well, if y sub p is a, y sub p prime is 0, y sub p double prime, of course, would also be 0. So we would have 2 times 0 minus 7 times 0 plus 5 times a is negative 29, which gives us 5a is negative 29. We equate the 5 to the 5a to the constant term. Solve for unknown coefficients. So the only unknown coefficient is the constant coefficient. So this one ends up being kind of an easier one. It only has one equation, one unknown. So we end up getting a is negative 29/5. And then we go ahead and make our general solution. So you form the general solution. So we will have, and this is from our step 3, so y is equal to negative 29/5 plus c1e to the 5x over 2 plus c2e to the 1x. Groovy? And we're all done. Woohoo! All right. So let's take a look at another example. So again, step by step, right? So step 1 was solve that homogeneous equation that's related. So we want to solve y triple prime plus 2y prime double prime plus y prime equals to 0. So using our groovy trick with the m's, we'll have m cubed plus 2m squared plus m equals 0. So then, factoring out an m, we'll get m squared plus 2m plus 1 is 0, which is m times m plus 1. The quantity squared is 0. So we get m1 is 0. And then we get m2 is negative 1. And that has a multiplicity of 2. Cool so far? So our complementary solution YC is going to be C1 for the m1 is 0, and then plus e to the negative x for one of the negative 1 solutions, and then plus c2 e to the negative x for one of the negative 1 solutions, and then plus c3 x e to the negative x for the other one. Cool, cool? All right, step 2. Annihilate. L at y equal to g at x. Okay, again, we just have a constant, okay? So D is going to be the annihilator. So you'll have d cubed plus 2d squared plus d equal to 10. And then the annihilator is d. So we will have all of that left-hand side equal to 0. And then step 3. Remember that we now want to find the general solution of the homogeneous equation. So, to do that, take it back to the m's. We'll have m times m cubed plus 2m squared plus m equals 0. Remember, we had factored out an m, so now we'll have m equals 0 with multiplicity 2, and then this was m plus 1, the quantity squared was 0. This is all from what we did before. So you'll get m1 is 0 with multiplicity 2, and we'll have m2 is negative 1 with multiplicity 2. So y equals to c1 plus c2 times x for that second multiplicity of that 0 solution, and then we'll have plus c3 e to the negative x plus c4 x e to the negative x. So we had already gotten, let's see, the c1 and these two terms. Those are from the yc. So the c2 times x would be the yp. Cool so far? Okay, so step 4, form linear combination of YP terms so our YP is just going to be A times X. So YP prime is A and YP double prime is 0. And of course, YP triple prime will be 0 as well. So when you form that linear combo, you'll have your Y triple prime plus 2Y double prime plus Y prime equal to 10. Well, Y triple prime is 0. Y double prime was 0, so you'll get 2 times 0. And then Y prime was A, and these should be, sorry, I should have these P's under here. I don't think I did that with the other one. You should put P for particular. All right. And then we would have plus YP prime was A, and that's equal to 10. Now, I know it's not going to make a difference for this one, but I'm going to add in 0 times my YP term, which was AX, and that's equal to 10. That's going to zero out. Step 5, when we solve for unknown coefficients, what'll happen is it'll again be kind of a so easy it's hard sort of thing. All that's left is an A on the left side and a 10 on the right side. So A must be 10. So for step 6, where we need to form the general solution, we will have, let's see what we had in C3. So we will have Y equals C1 plus 10x, because we solved for that YP. So in place of C2, we put 10, plus C3 e to the negative x plus C, actually it'll be C2 and 3, and C3xe to the negative x. And we're done. Cool, cool? All right, perfect. So now we've got another problem a little bit more involved, and this will be our last one of the day. So let's check it out. First step. Solve Y double prime plus 3Y prime minus 10Y equals 0. So going back to our trusty m's, m squared plus 3m minus 10 is 0. It turns out this factors will have an m and an m, and then 5 and 2 have a product of 10, and they're going to have different signs, so their difference is 3. And so having the 5 and the 2, I need the minus, the 2m to be negative and the 5m to be positive. So we'll get this right here. And so m M1 will be negative 5, and M2 will be 2. So y complementary is equal to e to the negative, oops, I forgot my c, sorry, c1 e to the negative 5x plus c2 e to the 2x. Cool? And then, now we annihilate. So this one will be a little more complicated, right? Got more going on than just a constant. So on the left, we'll have our second derivative plus 3 times that first derivative minus 10. And then on the right-hand side, I'm going to take a look at this. We have, I kind of like multiplying them out. So we've got xe to the x, and then we have plus an x, right? So since we have an xe to the x, we need an alpha equal to 1 with multiplicity 2, right? So this could be written as 1x, right? And because it has an x in front of it, we need that multiplicity 2. So d minus 1 squared annihilates xe to the 1x. D squared annihilates x, right? Because that would zero out that one. So we apply that d minus 1 squared and the d to the other side. We already know it's going to annihilate it, right? Because we've learned about that. If you want to verify that it annihilates, go right ahead, all right? But it will. So here we end up with d squared times d minus 1, the quantity squared, times d squared plus 3d minus 10 is going to equal to 0. Because I promise when you go through all that stuff, it's going to zero out. That's how it was designed. Now, next step. Find general solution So I need to take all of this, but remember we write it in terms of the m's. So we're going to have m squared times m minus 1, the quantity squared. We already factored the other one as what? M plus 5 times m minus 2, and that's all equal to 0. So we're going to get m equal to 0 with multiplicity 2. We'll have m equal to 1 with multiplicity 2. M equal to negative 5, and then m, so we can call this, I guess, m1, m2, m3, and m4 equal to 2, and those are distinct. So y will equal to c1 plus c2 times x from the m1 equal to 0 with multiplicity 2. and then plus plus C3 e to the 1x plus C4x e to the 1x plus C5 e to the negative 5x plus C6 e to the 2x. Long one this time, right? All right, so now step 4. This will be a little harder to solve. First we want to form linear combination of yp. So when we do that, well, what is yp? Yp, remember, is all of this, I believe. Yep, was yp. And this here was yc. So yp equals that whole thing, and instead of the ci's, we put a, b, c, and we'll put e instead of d so it doesn't look like a differentiator. So we will have, starting with that C4 term, we'll have ax e to the x plus b e to the x plus cx plus e. Cool so far? Now, yp prime will be, we'll have a e to the x plus ax e to the x for that product, plus b e to the x plus c, and the e zeroes out, and yp double prime will be a e to the x plus a e to the x plus ax e to the x plus b e to the x, and the c zeroes out. So that yp double prime will have 2 of those a e to the x's, and then 1 of the b e to the x's, and then an ax e to the x. Agree? All right, I'll go ahead and just add another page here. Now this one will probably bring it together for you more as far as solving for the coefficients, because there's more going on. So here we want to solve for the unknown coefficients in yp. So the original equation, remember, was y double prime plus 3y prime minus 10y. Y double prime plus 10y prime, nope, plus 3y prime, my bad, minus 10y equals, and we multiplied that out, e to the x, so x e to the x plus x. But aren't there some missing terms, right? So we'll go ahead and we'll add those in soon. Let's just go ahead and plug in, and these are sub p's here. So y double prime sub p was a, or 2a, sorry, e to the x plus b e to the x plus a times x e to the x. So I just got that from up there. And then plus 3 times yp prime. So yp prime, we had a e to the x. I'm going to put the b e to the x next to it. And then plus ax e to the x plus c. And that was from here. And then we have 10 minus 10 times yp, which was ax e to the x plus be to the x plus cx plus e. And all of that is equal to x e to the x plus x. So now we're going to continue to work through these, and that of course we found just from here. So now here we go. We want to work these things out, so we have 2a e to the x plus b e to the x plus ax e to the x plus 3a e to the x plus 3b e to the x plus 3ax e to the x plus 3c. And then I need to move this down. Sorry. Minus 10a x e to the x minus 10 b e to the x minus 10c x minus 10e. All of that equals x e to the x plus x. Now we'll start to narrow things down. I know it looks really messy, but trust me, it'll be better. So I'm going to put the terms that have an x e to the x first. So I have an ax e to the x. I have a 3ax e to the x. I can combine those as like terms. And I have a minus 10a x e to the x. So when I combine those, I believe I'll have negative 6 ax e to the x. And then if I go through and now combine the e to the x terms, right? I have a 2a e to the x, a 3a e to the x, so those combine to be 5a e to the x. But I've got a b e to the x here, 3 of them here, which would give me 4, and then minus 10 of them here. So combining those, I will have the quantity. So I'm going to put this in parentheses and you'll see. I'll have the quantity. I think we said that for our a e to the x's, we ended up having 5 of them. And then we had minus 6b of them, and I'm going to factor the e to the x to the right. All right, now what else do we have? We have the x term, and I think there's only one x term. So we'll have plus negative 10 times c times x. And then when we combine the constant terms, we'll have plus 3c minus 10, and this is a uppercase e, sorry, 10e. Now we have to add in terms that are missing. So we have 1 xe to the x plus 1 x. But we don't have our e to the x term, so let's move this guy over just because of the order we put it in. And then add 0e to the x, right? And then we have no constant terms, but we can say plus 0. And now here's the trick. You equate coefficients. So since negative 6a is the coefficient to xe to the x on the left side, it has to equal to 1, which is the coefficient of xe to the x on the right. So we equate negative 6a to 1 because they are coefficients to the same term xe to the x. And we would also equate 5a minus 6b equal to 0, because that's the coefficient to the e to the x term. And then, continuing, negative 10c has to equal to 1, because those are the coefficients to the x terms. And then three c minus 10e has to be 0 because those are the constant terms. And then you just solve this system of equations, which shouldn't be too terrible. Here we're going to get that a is equal to negative 1/6. From this third one, we'll get c is equal to negative 1/10. And then plugging in a as negative 1/6 to that equation, we would get negative 6b. Well, we'd have negative 5/6 that we'd be adding to the other side, so we would get 5/6. And then when we divide both sides by negative 6, we would get b is negative 5/36. And then similarly, plugging in negative 1/10 for c, we get 3 times negative 1/10 minus 10 times e is 0. Negative 10e would equal to positive 3/10, and that would make e equal to negative 3/100. And now we go back and find our general solution. So step 6, we already found it, we form the general solution, plugging in what we found for the constants for the particular. So here we go, y equals 2. So 2a e to the, that was y double prime, sorry. Yp consisted of E was that first constant, right? So let's see how we want to put this. Let's put the particular second. So we'll put C1 e to the negative 5x plus C2 e, was it negative 5? Yeah, e to the 2x. Now we're going to start with the particular. So we had a times x e to the x, right? Well, what was a? Negative 1/6. So minus 1/6 x e to the x. Cool so far? B was 5/36, and that was paired with e to the x. I'm getting it from right here. And then C was paired with x, and C was negative 1/10. And then we have our constant term, which is minus 3/100ths. And that's it. Isn't that groovy? All right, well, I hope you enjoyed the Annihilator section. Just love that name. All right, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, hit that like button and please subscribe. Bye.